Hello and welcome. We are continuing with Organic Chemistry 2 Review, Part 5, and this is presented to you by Science Visualized. Now, question number 1. Using the 4n plus 2 pi electron rule, this is also called Huckel's rule. So, Huckel's rule of aromaticity. For aromaticity, label the following structures as A for aromatic, Na for non-aromatic, or AA for anti-aromatic. So if you look at this structure, there are 3 rules that we need to consider. Number 1, is it cyclic? Number 2, does it have a continuous p orbital or continuous conjugation? Number 3, A, does it satisfy the Huckel's 4n plus 2 pi electron rule? And you'll see that if n is 0, then the 4n plus 2 becomes 0 times 4 is 0 plus 2 becomes 2. If n is 1, it becomes 6, and then 10, and then 14. And then 3b, 4n pi electron rule. If n is 0, then the number of electrons is 0. If n is 1, the number of electrons is 4 pi. And then if n is 2, it will be 8 pi, and then 12, like that. Okay, number 1, is this structure cyclic? Yes, it is. So that one is satisfied. Number 2, do you have a continuous p orbital? So that means you either have a double bond or triple bond, or you have electron pair, or you have a negative charge or a positive charge on carbon. So if you look at this structure, this carbon has a double bond, double bond, double bond, double bond, double bond. Therefore, that rule is satisfied. Last one, number 3. How many pi electrons? And when we say pi electrons, we count the number of electrons inside the ring. Each double bond is 2 electrons. But if you look at these double bonds, those 2 electrons are outside the ring, outside the ring, outside the ring. The only 2 electrons inside the ring is this one here. Therefore, the number of pi electrons is 2. Therefore, it satisfies the 4n plus 2 pi electrons, and therefore, it is aromatic. So, A for aromatic. If 3b is satisfied, it becomes anti-aromatic. Number 2, it says label the following structure as C for conjugated or non for non-conjugated system. Remember, conjugated system has alternating single and double bonds, or alternating triple bonds, like that. That's conjugated system. Or you could even alternate double and single. So like that, that would be conjugated, because see, you have alternating double bond, single bond, double bond. So in this structure, we have double bond, single bond, double bond, so that side is conjugated. On this other side also we have double bond, single bond, double bond, that's also conjugated. So A is conjugated. Remember, we're using C for conjugation. B, you have double bond, single bond, double bond. No. Double bond, single bond, single bond, single bond, double bond. So this is not conjugated, so we'll call that none. C, same thing. If you have at least 2 single bonds between the double bonds, it will be non-conjugated. Same thing with D, non-conjugated. Question number 3. It says provide a product or products for this reaction. And this is electrophilic aromatic substitution reaction. Remember, electrophilic aromatic substitution reaction, you have an aromatic compound with a hydrogen, and then when you react that with an electrophile, you end up substituting the hydrogen with electrophile, so you end up with an electrophile replacing the hydrogen. In this case, you have nitric acid and sulfuric acid. When you mix these together, you get NO2 plus. So plus charge on nitrogen, sometimes just written like this, NO2 plus. That's the electrophile. So you end up adding the electrophile to the aromatic position. But now we have to decide where the NO2 will add. If you look at this amine, it's an ortho para director. It's an electron activator because it has lone pair of electrons that it activates the ring by increasing the electron density, and therefore it will direct a new group to ortho. This other ortho position cannot happen because it's already occupied by an OH group, and then also para. So direct it to ortho and para position. Now, if you look at this OH, it's also an ortho para director, and therefore it's going to direct a new group to the position ortho with respect to OH. Remember, ortho is 1, 2, and then also 1, 4. That's para. Now we see that there's a disagreement because the amine is directing to this position and this position, while the OH is directing to this position and that position. But actually, NH2 is a stronger director than OH. So because of that, NH2 will win, and therefore we're going to add the new groups to that position and that position. So I'll go ahead and draw the product. We're going to have two separate products. And now the first one is this position. You end up adding the electrophile, that's the NO2. And then the second one is this other position. You add the electrophile to that position, which is para to the NH2, and therefore NO2 there. Those are the two products for that reaction. Next, we see that now we have NO2. This is an electron withdrawing group, as opposed to NH2 and OH, which are electron donating groups. So for electron withdrawing group, it pulls the electron density out of the ring, therefore it reduces the electron density of the ring, and therefore it deactivates the ring. It makes it less reactive. And because it's an electron withdrawing group, it's going to be a meta director. Therefore the new group will be directed to either this meta position. Remember, meta is 1, 3. So 1, 2, 3. 1, 3 position is meta, or this meta. But actually, if you add to either of those meta positions, it will give you the same product. Remember, we're using iodine and copper chloride, and that's going to give I plus electrophile. So you end up adding iodine to the meta position. Next question. It says label or identify the structures that matches the spectrum data shown below. So if you look at this spectrum, it's measured in parts per million, ppm. It's starting from 0 all the way to around 230. Anytime you start from 0 to around 230, it will be carbon NMR. So 0 to around 230 ppm. And then proton NMR is also measured in ppm, but it starts from 0 up to around 12 or 14 ppm. That's how you tell the difference. Also, carbon NMR is just single lines. You don't see any splitting. For proton NMR, you'll see things that look like that. For doublet, you'll see triplet, depending on the multiplicity, which is n plus 1. You use the n plus 1 rule. So in this case, this is carbon, there is no splitting. And for carbon NMR, you can just count the number of signals, and that will show you how many carbons are in different chemical environment. So we have here number 1, number 2, number 3, and number 4, meaning we have 4 types of carbon. And then we know that this one here, about maybe 220, so that one should be a carbonyl. So starting from around 160 onwards, that's a carbonyl. And then if you have an alkene, it will be in this region here. You'll see peaks in that region for alkene. And then if it's an alcohol, you'll see it around here for COH, or just carbon connected to oxygen. And then anything below that is usually alkanes. So between around 20 to 0 is just primary alkane, carbon. And then around 20 to 30 is secondary, like that. So let's just use the number of signals. We see that we have 4 different types of carbon. If you look at this structure A, we have 1, 1, 2, 2, 3, 3. So that has 3 types of carbon, therefore that fails. Structure 2 has 1, 1, 2, 2. Has 2 types of carbon, fails. Structure 3 has 1, 1, 2, 2, 3, 3. So 3 types of carbon, that fails. And then structure D has 1, 2, 3, and 4. has 4 types of carbon that passes, and we can confirm. See, we have a carbonyl here, and that structure has a carbonyl, and then the rest are alkane carbon. So carbon number 2 will be more deshielded, it's going to be more downfill, so it moves that way, and that one is most likely going to be this one here because it's next to a carbonyl carbon. So the right answer is going to be D. Number 5, identify the 2 main functional groups according to the IR spectrum. For IR spectrum, there are 2 key things you look at. Number 1, the region between around 4,000, actually from 3,500 to about 1,500, so 3,000 to 1,500, wave numbers is in per centimeter. That region is called functional group region. Then after that, this other region is called fingerprint area or fingerprint region. Fingerprint is not very important for functional groups except for something like C or C. It's because there are so many signals in that area, it's not easy to identify the functional groups in the fingerprint region, and therefore it's just used for direct comparison. If you think 2 compounds similar or alike, then the fingerprint region has to match. The most important region for functional group identification is that region there. So this one here, the functional group region. If you see a broad peak around 3,500, so you see something that looks like that, that's an OH. We don't have OH here. If you see around the same area, slightly maybe lower, around 3,400, you see something that's like that, medium intensity, that's going to be NH. NH2 will split into 2. And then around 3,000 is CH. So this area, like what we have here, that is CH. Around 2,100 here, this region, that's triple bond region. So you have carbon-carbon triple bond or carbon triple bond nitrogen. And then the other important area is around 1850. So I'll say this one here. 1850 to around 1680 wave numbers. That's carbonyl area. And that's going to be strong and sharp absorption. So let me just talk about the intensity. If that's the baseline, if something is closer to the baseline, we call that weak. If something goes all the way to the middle, that's medium intensity. And then it goes all the way down like that, that becomes strong. And then all these are sharp. If it's broad, it's going to look like this. And that will be broad. So in this case, we have 2 functional groups. We have a CH and we have a carbonyl. So the main functional groups here are CH and carbonyl. Last question. Given the spectrum, if it's single, it's a spectrum below, identify, this is actually a mass spectrum. The units here should be m/z, which is mass to charge ratio. Identify the parent peak. The parent peak is what you have before the molecule starts splitting, and therefore it's going to give you the molecular weight. So that will give you the molecular weight, and that's usually farthest to the right. So if you see farthest to the right, we have that small peak there, and we have this one here. So that is most likely going to be the M+, which is the parent peak. And that one, it's at around, say, 1, 2, 3, 4, 44. So m/z equals to 44. The next one, this one here, is 45. That's usually due to carbon 13 isotope, 13 carbon isotope. You know, the ratio of carbon 12 to carbon 13 is about 99 to 1. Next, parent ion. Parent ion and parent peak is the same, so m/z equals to 44. Molecular ion is the same thing as parent ion or parent peak, which will be m/z equals to 44. So molecular ion, also called M+. The other thing that's not included here is the base peak or base ion, and that's usually the tallest peak. The tallest peak will be this one, has 100% abundance. and that one is m over z equals to 29. So that will be 29. And then the possible structure, we know that the molecular weight is 44. If you look at this, at the fragmentation pattern, you'll see that we have 15. That's usually CH3, because carbon is 12 plus 3 hydrogens, that gives you 15. And then we also have 29, which is CH3, CH2. So 15 plus 14. And then the next one is 44. So that the difference between 44 and 29 is actually 15. So that means you just add a CH3. So the structure will be CH3, CH2, and CH3. Thank you very much.